Lab 3, Black Hole Orbit by Shannon Schechter. The object of this lab was to determine the mass of the black hole by using the black hole's initial position, that it's going to be 4 e to the 10, negative 1 e to the 10, and 0 meters, the changing position data from an orbiting star, that it's going to come from a CSV file given to us, and the star's mass, that it's going to be 1.98 e to the 30 kilograms, and the net force that we're going to calculate later on. Using CSV file to estimate the mass. By programming BPython to get the data from the CSV file, we can quickly calculate the change in momentum. So we're going to use different positions to get the change in velocity, and with the change in velocity, we can get the change in momentum. For this lab, we used Newton's second law, that is going to be the final velocity equals the initial velocity plus the net force divided by the mass and multiplied by the change in time. The position equation, that it's going to be the final position equals the initial position plus the velocity average times the change in time. The momentum principle, that we're going to say that the net force equals dp dt, and dp dt can be divided into the parallel component and the perpendicular component. The parallel component is responsible for the speeding up or slowing down of the object, and the perpendicular component is responsible for the changing direction of the object. Since Fnet is equal to dp dt, then Fnet can also be divided into Fnet parallel and Fnet perpendicular. The gravitational force law, it's going to say that the net force equals g times the mass 1 times mass 2 divided by r squared. So for this lab, r is going to be the black hole's position minus the star position. The mass 1 is going to be the mass of the black hole. The mass 2 is going to be the mass of the star. And g is going to be the universal gravitational constant, 6.67 e to the negative 11. Now I'm going to show you the code. We started the code with the initial conditions, the star's mass that we already said before, g, delta t that it was given to us, and we're going to start the time at 0. We can see that we're going to get the position from the CSV file, and with the different positions, we're going to do a while loop to calculate the initial velocity, the final velocity, and with these velocities, we can get the initial momentum, that we're going to use the star's mass for this, and the final momentum. Delta v is going to be the velocity final minus the initial velocity, and delta p is going to be p final minus p initial. dp dt is going to equal the change in momentum over the change in time, and this is accurate when the change in time is very small. And with this while loop, at the end we're going to calculate the net force, that is going to be equal to dp dt. We are going to know that dp dt parallel component is of momentum is calculated by taking the magnitude of dp dt and multiplying it by p hat, that we can see over here. And the Fnet parallel is going to be equal to dp dt parallel, dp dt perpendicular equal to dp dt minus dp dt parallel, and Fnet perpendicular equal to dp dt perpendicular. Now we're going to see that the black hole's mass is going to equal the magnitude of the net force times the magnitude of r squared divided by g when multiplied by the star of the mass. And now we're going to run the code. And we can see that Fnet is going to be the yellow arrow, and it's going to be pointing towards the black hole, which is the direction of the gravitational force, so this should be correct. And the black hole's mass was 3.56 e to the 31. Now, for the different questions, the difference between Fnet and its components and dp dt and its components is a cause and effect relationship. So while the values might be the same, the force does the push or the pull that causes the change in acceleration and velocity, which eventually will cause the change in momentum. And if a star's motion remains unchanged in the presence of the new black hole, then we will have to conclude that the black hole's mass is the same as the one we calculated on this lab. Thank you.